Okay, so my name is Tomas Patricek, and I'm going to talk about a project that I worked on during internship at Microsoft Research with Don Syme. I'll start by talking about something that you can do in F# already, and then I'll talk a little bit about one experimental language extension that I did for F#. The topic of the talk is going to be concurrent and reactive programming. I'll focus more on the reactive programming part. What does that mean? What does reactive programming mean? So I guess that's a little bit difficult to define, but I'll be talking about how you can write applications that don't necessarily do a lot of computations, but need to handle lots of user events and things that happen somewhere in the world. And the interesting thing is that both reactive and concurrent programming, there are so many libraries that you can use from languages, but it's difficult because you usually want to use them in some mode. But when you have too many libraries, it's difficult to select what do you want avoid using. So I think that languages can help with that. There are many languages that support some concurrency or reactivity as a language feature, but I also think that we should do this without the language specifying directly what kind of concurrency mechanism or reactive programming mechanism is it using. So I'll talk about extension that lets you encode various different programming models in F#. And I'll start talking about asynchronous programming in F#. You've seen that in the previous talk. Just a few points that I think are important. The async workflows in F#, that's not a language feature. That's just one case of a more general feature called in F# computation expressions. Many of you will probably recognize monads because that's a little bit, well, it's in many ways the same thing, not in all. So that means you can define blocks like this, and there's some object that's called builder, and that defines what does the let bank in the expression mean, and it lets you compose like primitive blocks of code in some non-standard way. Here's one other example than asynchronous workflows. So you could, for example, define a nullable computation builder, which propagates null. So if you had like load customer method that returned customer, it could also return null. And you could define nullable builder like this that would propagate the null value. So if the first method returned null, the whole expression would return null, and it wouldn't run the next line. That's also that's just a variation of maybe monad in Haskell, so that will be familiar to some people. But it's important that you can define your own computation expressions. And asynchronous workflows are just one case of that. That's supported in the F# core libraries. And it's designed for writing code that doesn't block actual .NET threads. So in this case, we're doing some HTTP web requests. And the bang here means start some task or start some asynchronous operation and resume the workflow when it finishes. The asynchronous workflow isn't alone isn't alone a feature to do like parallelism, but it's used in that way because you can easily encode things like fork join parallelism using them. So this async.parallel that spawns multiple workflows and then joins the results. But you can use it for encoding many other like concurrency patterns. Yeah.
Is there any ability to set an alternate timeout on a given async computation?
I'm not sure if there's a way to set a timeout currently, but in principle it should be possible. Maybe Luke can answer.
Where you run it, you can tell the timeout. So the async itself just describes a computation that could happen, but when you run it and you start it executing, you can say, I want a timeout after a certain.
For any particular async block?
So this code here, for instance, doesn't actually do anything yet. It just creates the ability to do something. But then later you'd have to say async.run pages, right? And at the point where you said async.run pages, you would then pass a timeout that you wanted for all of them.
But that would be for all of them, I meant for a single block.
Oh, sure. Then you'd have to compose together, basically say how you wanted each to go. I don't know where the...
So the thing here is a list of asynchronous workflows, and you could wrap it in an asynchronous workflow that runs workflow with time limit.
So you could certainly write a version of Parallel that does that. I don't know if our library Parallel function does that.
Yeah. Yeah, so now I'm going to move to reactive programming. And the point is that asynchronous workflows can be used, or one of the things they can be used for is expressing reactive code. And that means you will have some concurrently executing agents that will run, the whole thing will run on a single thread, as opposed to concurrent programming when you have multiple concurrently executing threads. And that's because, so the reactive programming part, that could be used, for example, for one part of the application that's mostly concerned with user interfaces, and that doesn't do any difficult computations. You could probably have like the other part that runs some computations concurrently, but the pure part that deals with the GUI, that doesn't have to be multi-threaded because it doesn't do any real work. And the problem is just how to write it in some reasonable way so we don't, so the language doesn't force us to block and wait for something. So I'm going to show you how to write GUI components that are composed from various agents that most of the time just are waiting for some events. And when the event occurs, they will do some quick reaction, update the GUI, and then again start waiting. So one example of this would be a simple agent that counts the number of clicks on some control. And we can write it as a recursive loop in F#. That's inside implemented as an asynchronous workflow. And what the workflow would do is that it will wait for an event to occur. So it will block the workflow, which doesn't mean blocking any threads. And when you click on something, it will resume the agent, and then it can handle some reaction to the event, increment the counter, update the label, and then there's a return bank primitive, which means, which is technically speaking just a tail call. It means that it will then continue looping with the asynchronous workflow that you give it. So the whole thing is some asynchronous workflow that blocks only at this point. And when it blocks, it waits for the event. Then when the event occurs, it does some code that's executed very quickly. And then it again gets to the point when it's waiting. And we can use, if it's a recursive function, then we can use the function arguments to represent some state of the agent. So that's pretty much typical functional programming pattern. And in this case, this code looks like it's just aggregating some events. That's true. We could have some simpler primitive for writing aggregation. In fact, F# library does have that. But that works only if we have some relatively simple problems that we want to express. So, for example, if we wanted to change this so that the rate of clicks that is counted is limited, meaning that after every click, any clicks that you do within 1 second will be ignored. Then it's no longer just a simple aggregation of click events, so that's difficult to write. But if you use something like this asynchronous workflow, then adding this rate limitation is really easy, because the only thing you need is to do something like this. And that means, so now in the code there are 2 blocking points where the asynchronous workflow stops executing, waits for something. And again, this waiting doesn't block any threads, because it just schedules some function to be called when the event occurs. So the whole thing is running on a single thread without blocking. Yeah, so we have one waiting point, which waits for the mouse down. Then it does some processing. And then we have second waiting point, where we are waiting for 1 second. This reactive sleep that creates just the basic workflow that resumes the agent after 1 second. Yeah?
I still don't understand quite why you have the bang there, because it seems like reactive wait event should wait. So what's the bang doing, and what would happen if you left it off?
Yeah, so the bang, let bang means, so the code that's written without bang, that's just a basic F# code that's running, and the bang lets you, so the bang is a thing that's defined by the asynchronous workflow. And for asynchronous workflows, bang means that we're starting some operation that will call us back when it completes. So that means the primitives, reactive.primitives, can just schedule some, can register some callback to be called when something happens. So this waiting for mouse down, that would, if you didn't have bang, if you just wanted to wait for mouse down, then it would block the thread, because the thing by default is running on a, the code, the standard F# code is just a code that runs on a single thread. And when you're waiting, it blocks the thread. And the let bang lets us insert like asynchronous calls inside the code.
The question is whether the implementation has to deal with the continuation being passed back by the reactive await event, or whether there's a runtime like concert underneath that deals with blocking and unblocking continuation. If you did this on concert, you could get rid of all the bang.
Yeah. So that's probably the problem with .NET, where you don't have direct support for continuations. So async is essentially an F# implementation of continuations. Yep.
So under the hood, does the letbang essentially, I mean, since it all compiles down to MSIL, is it essentially an equivalent of just the APM in .NET where it's just begin, sync, end sync?
Yes, basically. It's slightly different because there's some F# type that represents that, but it can be thought of as .NET APM. Yeah.
Use doBang since you're not taking care of, since you're not paying attention to the return value from
Yeah, I could use doBang. I just didn't want to introduce second bank primitive. But yeah, I could. Yeah.
It's not quite clear to me. Maybe I missed something, but isn't it when you call sleep, you actually still keep the thread around? It just switches to another thread, but it means that the whole thread is dedicated to this little procedure.
So the sleep here is actually it just creates a timer that after 1 second calls the continuation through the GUI thread.
So it means that at this moment we really save the continuation and release the current thread?
Yes. Yes.
So the computation expression in F# is basically a monadic bind, and all the subsequent things are bottled up as a continuation if it's past something. And so we're just scheduling callback that when this event happens, we'll get the thread back and actually do the continuation. But it's all syntactic sugar for breaking up all the individual lines of code into continuations.
Yeah. So when you do bang, it just schedules registers the continuation, and then either keeps running other agents if there are some events unprocessed, or just, yeah.
Sorry. In this case, these are typically going to be the CLR threads, right? So the so-called soft threads. Are you really saving anything since those are virtual threading anyway, whereas the hard OS threads aren't really being impacted by this?
So in this case, the thing is running on a single thread, on the GUI thread. And I'm not trying to save any threads. I'm more trying to give you a better way to write reactive programs that don't need multiple threads.
So for reactive programs, there is a benefit to be able to stay on the UI thread all the time, right? In the programming model at least.
We're not going to block the GUI, but
Sure, but you don't have any direct control over that.
Well, here you do, right? Because you're not ever.
No, you don't. The CLR is going to decide which thread you're on.
No, because the thread you're on, that's decided by the primitives that you have in the code. So async.start, that's some primitive that starts the computation runs first block of the computation on the GUI thread. And when the first block reaches this let bang point, it just runs some primitive that you wrote. That's the await event. And await event registers handler for the event. And the event triggers the handler on the GUI thread as well. And this is implemented in the same way. So it triggers the handler. Yeah.
In a similar way that event-based programming tends to fire events on the UI thread because you're likely to do some UI updates. When you're doing this reactive programming.
It's always on, right?
Yeah, it's always. So similarly here in a reactive framework, using async to really do the same thing.
Right. So the problem is, how can we easily describe agents like this? What's the mental concept for writing agents? And I think the important point is that the best way to think about agents is as a state machine. So the previous example, that was just a state machine with two states. The agent starts, and then it waits for the event. Then when the event occurs, there's a transition into second state where it waits for something else. And then there's transition back to the state where it waits for the clicks. An important point is that when we are waiting for sleeping, when we are in the sleeping state, we are waiting only for the timer to complete. But all the click events are dropped. They're not cached in any way because we're not interested in like listening to them. So the events are used only to trigger the transitions in the state machine. But we need one more thing, which is the ability to select between 2 or more transitions. So here, that's an extended version of the sample that also lets you press the key to enable or disable the counter. And from the active point, we can either wait for key press to switch to the inactive state, or we can wait for mouse down to increment the counter. And the way we can write this, so an important point is that you can't write this using the single, using the await event primitive that took single event, because that's just outside of the language you can express using that. So we need some other primitive. What I have here is await event overload that takes 2 events and calls or resumes the agent when the first of them occur. So you would probably like to write something like this. We wait for key press and mouse down, and when we got key press, we do something. When we get mouse down, we do something else. But that's not that easy to write in F# because this code that doesn't make much sense. Because what's the return type of the await event primitive? It has to be something that can be either one value, that's the value carried by key press, or the other value. So currently in F# you would have to write something like this, which isn't as nice as it could be. So the language extension that I worked on lets you write this more easily. So the let bank in this code that represents bind from monads, and we need something like the ability to wait or to bind on multiple values. So we can change this to something like this. And now the match bank, that's just a general version or more general version for the let bank primitive, where you're waiting for multiple events, multiple values, and you can write some patterns here. So the bank key E, that means I want to wait for the occurrence of the event, and underscore means I don't care about whether the event occurred or not. So if we get key press event, then the first pattern is matched because we got some value from the key press, and we don't care whether mouse down occurred or not. So the meaning of the matchbank primitive, that's done in exactly the same way as the meaning of let bank. So the author of the computation expression specifies what that means, which means that it's a general language feature. In this case, it means wait for the first event that matches the pattern. But an interesting point is that it's more expressive than just selecting between 2 events. I'll just quickly go through this, but you can, for example, wait only for events that match some pattern. So you would throw away all other values, throw away all other occurrences of the event. If you had some state changed event, then you could perhaps wait only for the occurrences where the state is completed. Or that's more interesting thing, you can wait for 2 events to occur. That doesn't mean that you're waiting for two events to occur at one point in time, because that doesn't make much sense. But it can mean something like when you start listening, then wait for the first pair of events that matches the patterns here. So this could mean if you start with mouse down, then move the mouse, and then do mouse up, you'll get the pair of matching mouse down and mouse up events. So that's quite an interesting thing. Yeah, and so the one thing about these reactive agents that I've been writing here is that their type is just something like async unit, which means computation that you can start, and it does something. But it's very imperative in a way that the agent has to do all the effects imperatively. So these arrows would mean do something with the world. But very often you don't want to do something with the world. You can have agents that just wait for some events and return some event as well. So like you can have filtering agent that takes event as an input, gives you event as an output, and triggers the returned event only like when the value matches some predicate. So we can do this because we can define our own computation expressions. So I'm going to use my implementation of async that's slightly different. And we can have this yield primitive here, which means, so the returned thing now isn't async of unit, but it's event stream of some values. And yield means trigger the returned event. So in this case, we have, again, the counting agent. But instead of doing some imperative thing, it would trigger the returned event stream every time the count changes. So this way of writing code is quite composable, because you can compose the program from these agents that have some local state, but are quite pure in some sense. And the only imperative thing would be at the end, where you often need to do some like update of the GUI when some chain of event streams yielded some value. Yeah. So do I have 1 minute? No. 1 minute. The interesting thing about this is that it's a general language feature, so you can use it for various other things. I've talked mostly about the reactive programming, but you can use it for concurrency as well. So if you're programming with futures, future is just a computation that eventually gives you a value. It's not quite clear how does it relate to F# async, but it's definitely used differently for CPU-bounded concurrency. Then instead, so that's a sample that would calculate product of all leaves in some tree. So you calculate product of the left subbranch, the right subbranch, and then multiply them. If you wanted to do this in parallel, you could implement something like future computation expression and provide the match implementation that starts these two computations in parallel. And then you can use this joining pattern to wait for both of the results to complete. So that's just a slightly nicer syntax for the thing you can do in many other ways. That's not alone that interesting, but you can also write patterns like this, which means when the first task completes and it gives us 0, we don't care about the second task. So the underscore means we don't care about the value. We don't care whether it finished or not. And if the second one returned 0, the first one is still running, then we can directly return 0 because that's what the result will be regardless of the second task. Yeah. So I'm going to skip this, but if you know C omega and joint calculus, you can encode this using matchbank as well. Yeah, I'll be here, so you can ask. And the summary of the talk is, I think that, well, I'm not going to say that we don't need concurrency, but there are many interesting, many parts of the application where you can do well just by using single thread. I think that it's pretty essential to have a direct way to encode state machine when you're writing this kind of programs, because that's, I guess, the easier way to think about the problem. And I think that it's important to have, if we have some language extension like this, it's pretty important to have it generally useful. And thanks to many people who helped me and who I had a chance to talk about this during the internship. Yeah, so if you have any questions, I think maybe we still have some time for that.
You mentioned adding language support, so you actually hacked F#.
Yes, that's a change in the F# compiler, the match bank primitive. It's about, no, it's a experimental research project that's not going to be in F# anytime soon. But if we are going to have some open source version, then maybe it will be available. That's the state.
Remind me of Erlang.
Yeah.
Pattern matching in events.
Yeah, I'm not sure how that works in Erlang, but in Erlang, yeah, in Erlang you can have you can pattern match on the messages. So that's there's an F# implementation of mailbox processor in the library, and it turns out you can use this matchbank feature to simplify that a little bit as well. So that's definitely related. Yes?
If I've got this right, using match, you could say, wait for this one event or this pair of events. Or
Yes.
that would be rather hard to do in Erlang, I think.
Yes. So, yeah, that's quite related to the join patterns, because in join patterns, you can you can choose which of the channels you want to wait on. And Erlang is a bit like a join pattern with only one channel. So, yeah.
And what has the match pling construct that should just be syntactic sugar for calling other things? What's the one new thing that you've added that lets you do that?
Yes. So that's the tricky question. I guess if anyone's interested in talking about that, I'll be happy to get some good suggestions how to do it correctly. In the version I have, I just added match method that takes all the it takes like all the parts of the syntax as arguments. So the patterns are translated to something like a function that takes the value and returns bool, whether it succeeded or not. The underscore and the bank, which expresses whether you're waiting for the event or whether you're ignoring the value, that's translated to some option type. But I spent last week at Microsoft Research trying to figure out what would be the right set of primitives that let you encode this. I have some ideas, but I'm going to work on that a little bit more. Yeah.
Is this in-order matching? In other words, it goes top to bottom, or could it be best match?
So that's up to the implementation of the match bank primitive. But it's top to bottom after. So like in this case, when you got a value from one of the features, it would run them from top to bottom. So if you had like two same cases, it would always run the first one. But if you switched these two lines, it wouldn't wait for both of them. It always tests all the clauses when the current state of the values that we've got changes. So it tests the patterns multiple times. It re-evaluates the thing when one of them completes and when the second one completes. Yeah. So any other questions? Yeah.
So is there, if I understand that correctly, is there an implied precedence in the order I declared or not?
Sorry?
Is there an implied precedence in the order I declare those or not?
There's precedence in the order in which you define these patterns. Yeah, so the match primitive gets a list of clauses. So there's some order in that. But it's up to the implementation whether it respects the order or not. But it seems like a good idea, perhaps, to restrict this to force the implementation to respect the order, because that's what you would expect from the ML language. Yeah. So if that's probably all from me. So thanks for your attention.